Well, should we talk about math?
Yes.
Ask a question?
Yes. You just did. You want to ask two questions?
Just one.
Okay. Well, the first question is, may I ask a question?
Okay. Is the difference between an algebra and a sigma algebra that a sigma algebra allows constantly infinite unions?
Yes, absolutely. The entire rationale for it. A set algebra, if you take a set X and form a power set of all subsets, and then you select a, that's Gothic A, okay? It's a subset of the power set of X. So it's a family of sets. And if the following things happen, you call A an algebra of sets. First of all, X has to be in it. Second of all, if A and B are in it, that implies the union is in it. Right? And the third thing is if A is in it, that implies the complement of A is in it. That's an algebra, A. Okay? You can use De Morgan's rules on these two to show that means that intersections are in it as well. There are structures more primitive than this, called set rings of sets and semi-rings of sets that enter into measure theory. We'll probably bump into them someday. We might even bump into them when we talk about today. If you want to have a decent measure theory, you might want to have countable unions of sets. And so you say if AI is in A for all I in N, that implies the union over I of the AIs is likewise in L. When you do that, that's a sigma algebra. Sigma stands for, usually connotes a sum. Union and sum are sort of the same thing here. Sum of sets is a union of sets. So you build measure theory on sigma algebras. If you have a sigma algebra of sets and a measure and a ground space of which these sets are subsets, you call that triple a measure space. And then you can map that into a topological space and have a measurable function and make integration on that. Yep. Okay. Did you get the thing I sent you about compactness?
Yeah, I was reading about that.
Okay. All right. Well, tell you what. Let's see if we can slam dunk some other Cauchy stuff here. So we are basically on page 35, and what did we find? If a function is going to be Cauchy integrable, the following thing has to happen. The limit as the norm of the partition goes to 0 of the sum 1 to infinity, sorry, 1 to n, f of x sub k minus 1, that's the left endpoint. You can construct this whole theory on the right endpoint too. Delta x sub k has to be some number. And how did we get that number? What did we do? We had a special series of partitions whose norm did approach 0. Remember, the norms were 1 over 2 to the n. Yeah. They got smaller and smaller. And then we had a Cauchy sequence. These are real numbers. So we had a Cauchy sequence of real numbers. The real numbers are complete, so Cauchy sequences converge. So we were given this limit by the Cauchy nature of the sequence of Cauchy sums. And then we showed that once you get below here it is in words. Cauchy sums for small small norm partitions are close. That was the theorem, right? If you get small with the norm of the partition, any two are never more than this apart, right? If you're integrating from A to B, we showed that the difference between a sum based on this partition and a sum based on the refinement of that partition is never more than epsilon times B minus A. So if you have two totally unrelated partitions, you get their common refinement. This differs from this by no more than epsilon, this differs from this by no more than epsilon, so this differs from this by no more than 2 epsilon times B minus A. And that, friends, is the criterion on page 35 for Cauchy integrability, which we kind of stumbled into the other day. Continuous function on the interval AB is Cauchy integrable if and only if for each epsilon greater than 0 there exists a positive constant delta, so that if P1 and P2 are any Cauchy partitions of AB whose subintervals have length less than delta, in other words, they're partitions with small norm, the associated Cauchy sums are within epsilon of each other, right? Well, all you have to do is make this epsilon prime, and that's the epsilon they're talking about. You tell me how big the interval AB is, and what epsilon you'd like. And if we can go out and find this condition where every difference of Cauchy sums, where the partition norm is sufficiently small, every difference like that is absolutely less than epsilon, then the function is Cauchy integrable. So you'll see this again in the context of Riemann integration. This is called Riemann's condition. So you get two sums close together, arbitrarily close together, then you know that the function is integral in the Cauchy sense here, than it will be in the Riemann sense later. Okay? So if f is continuous, then the absolute value of f is continuous. Now, why is that true? Here's what they're trying to say. If f is continuous on AB, then the Cauchy integral exists, and also the Cauchy integral exists, but not vice versa. Let's examine why that's true. So if the function is continuous, the absolute value integral exists as well. But if the absolute value integral exists, maybe the function integral doesn't exist. That can happen. You can see how that would happen. They sort of tell you right there how it does. The loose end here, there's a lot of loose ends in Perth. Stuff he doesn't explain. This is one of them maybe. Why is it that the absolute value is continuous if the function is? Mothership is calling. Here's the theorem. Would anybody care to assist me in proving this? That's the theorem. Of course, if it's continuous on AB, then it's Cauchy integral.
Won't that come from the triangle?
How's it?
You can have some kind of function of flip side, some fact over the interval that the absolute value is regular.
No, yeah, that's exactly. Yeah, the Dirichlet salt and pepper function is the counterexample of this. You know, not exactly the case here. If f is 1, if x is rational, -1 if x is not rational, then absolute f is the constant 1 function, which is nicely integrable, but f itself is a disaster. So yeah, that's the counterexample that shows the converse isn't true. So just because the absolute value is integral doesn't mean the function is. But the forward direction is true, and why is that? If f is continuous, why is f absolute? Can we prove that? Bring very much paper.
No, Mark, this is gonna hold that.
Oh, wait a minute, I'll go through this on the other side, and then I'll talk to you about that.
I get